Alright. What is this from? Did we do this in class? This is from my final review. I don't remember what this is.
It looks like it was a problem in the practice sheet. Was like bring the true elements to the front, the false elements to the back.
Oh, yeah.
Yeah.
Yeah, this one was all left is less than right. Yeah, I don't even know what this means.
Maybe the other way around.
Anyways, yeah. But yeah, I think that is it. Anyways, so I went ahead and wrote this up beforehand. So we're going to walk through this. Alright, so part of our exam is graph algorithms, of course. But as we know, trees are also graphs. So we're going to walk through graph algorithms, working on graphs, and then also trees, binary search trees, and whatnot. Right. So as we know, this is a graph. It contains a set of vertices and a set of edges, and graphs can be undirected and directed. Undirected meaning that if you have an edge between two vertices, you can take that edge either direction, right? But if it's directed, let's say it's like this, and there's an arrow pointing that way, you can only go that way and you can't come back, okay? And then graphs can be unweighted and weighted. So let's say you have a graph like this. There's going to be some weight in the middle. Let's call it 6. That's going to be how much it costs to take that path from one vertex to another vertex. Okay. All right. So now we're going to go over performing depth first search and breadth first search on a graph. So with depth first search and breadth first search, when it's on a graph, not a tree, if it's on a graph, you can start at any vertex. Okay. If it's on a tree, you must start at the root. So like that. You must start here. But since it's on a graph, you can start at any vertex. I recommend just starting at the lowest valued vertex. Like here, we would start at 1. But if you wanted to, you start at 6, you can start at 4. It's up to you. It doesn't matter. Okay. So now, for breadth first search, what we're doing is that we want to start at some vertex, and then we want to visit every other adjacent vertex. Okay. And then from there, we want to visit the vertexes of the other adjacent vertices in the order that they were visited. So let's say we visited 1, 2, 4, 5. After visiting 1, 2, 4, 5, then we want to visit 2, 7, 6, 3. All right, because it's just the order that was visited. We visited 2 first, then 4, then 5. Let's say 4 had a child right there. We'd visit 1, 2, 4, 5, then 7, 6, 3, and then this one. Because they have to be in the order that they came. And we see an example of this with BFS. We start at 1, we go to 2, 4, and 5. After hitting 5, that means that we've explored everything on 1 because we went to 2, we went to 4, and we went to 5. Now we're going to go to the first one we visited from there and visit all of those. So after 5, we get 7, 6, 3. You can do it in any order. It could be 3, 6, 7. Doesn't matter when it's a graph. When it's a tree, it does matter. It has to be left to right. But here, it doesn't matter. So let's write that too. We do 3, 6, 7, or 7, 6, 3, or you could do 6, 7, 3. Once that's done, 2 has been fully visited. So we go back. Once 2 has been fully visited, we go back to 1, and then we visit all of 4. Okay. Nothing is on 4, so it's already visited. So we go to 5. Nothing is on 5, so it's already visited, and we're good. Okay. Does that make sense?
Yep.
All right. He can ask anyone give example. Wait, for the DFS and BFS, what kind of algorithm can he ask? Anyone give an example? I mean, I don't know. Again, I really don't know what question 2 is, I don't know what question 2 on the final thing. I don't know what he's talking about. I probably should have asked him for more clarification, but I was just too lazy. Okay. And then, so that's BFS. What DFS is, I think you have to come up with your own algorithm. Yeah, I don't know. What DFS is that, again, we can start at any vertex in a graph with a tree. Remember, you're starting at the root, right? But here, we are starting at the 1, just because. We can start at any vertex, but here, maybe he wants us to write an algorithm in steps, and then for an extra credit, we have to translate into code. Probably, I don't know. I think for that question, you should also remember what a complete graph is, what a balanced graph is, because he may ask you to write an algorithm to find out if a tree is balanced, write an algorithm to find out if a tree is complete, stuff like that. All right. So again, DFS is that we start at one vertex, then we visit one adjacent vertex. Not all of them, just one. And then once we visit that one adjacent vertex, we visit one adjacent vertex that's adjacent to that, and so on, right? So if we're starting at 1 and we go to 2, then from there we can visit 7, but once we hit 7, we realize that nothing's adjacent to it, so we go back, and then we can visit 6. We realize nothing's adjacent to it, so we go back to 2, and we visit 3, but nothing is adjacent to that, so we go back to 2, and then 2 has been fully explored. Once 2 has been fully explored, we go back to 1, then visit 4, and everything is adjacent to, but nothing is adjacent, so we go back to 1, then we go to 5, nothing's adjacent to it, so it's fully explored, and then we go back to 1. Okay. Once we're back at the original vertex, that means we are done. And here is an example of it, where we go from 1 to 2, from 2 to 3. Nothing's there, so we go back to 2, go to 6. Nothing's there, so we go back to 2, go to 7. Nothing's there, we go back to 2, and then go to 1. Once we're back at 1, we go to 4. Nothing's there, so then we go to 5. Nothing's there, and then we're back at 1. Okay, so again, here's a more detailed explanation. Begin at a start vertex and explore one adjacent vertex, then explore that new vertex. By explore that new vertex, I mean just visit one of the adjacent vertexes or vertices. And then that is how you do DFS on a graph. So again, that's BFS and DFS on a graph. Are there any questions about that? We'll do a more clear example, but are there any questions about that?
So BFS checks every adjacent vertex, and DFS checks the sort of route to all the children.
Well, here there's no root; it's a graph.
Well, I mean, I get it's a graph, yeah, but it's every from parent to child, every parent.
Here we're just saying with BFS we are checking every adjacent vertex, like you said, and then checking all of those adjacent vertexes. With DFS, we're starting at one vertex, then just visiting one of its children. Once we're there, we just visit one of those children. If there's nothing there, then we backtrack and go to the next child, backtrack, go to the next child, backtrack. No. In a graph, it doesn't matter. In a tree, it does.
Okay.
For BFSQ and for DFS stack, right? Yes. Correct. All right. Any other questions about that? How did you decide to go to 2 first rather than 5 or 4? Again, it doesn't matter. If we're here, we can go here, then go back, then go here, then go back, then go here, then go back. I just wanted to kind of outline that we can go to 2 and then go here and then here. If I did it with 1, 5, 4, then 2, it would kind of look too similar to BFS. That's why I chose to go 2. But again, if you wanted to, you could still go to 5 and 4. I just chose 2 for explanation purposes. All right. So here's another example. This is with a tree. And again, with a tree for BFS, we are visiting all of its adjacent vertexes. So we start at the root. We visit the adjacent vertexes, but first we visit the root. So 1. Then we visit the adjacent vertexes. That's 2 and 3. Then once we do that, we visit 2's adjacent vertexes. That's 4 and 5. Then we visit 3's adjacent vertexes. That's 6 and 7. So 6, 7. Now I want it to be a bit clear that once we hit 7, then we check 4's adjacent vertexes. There's nothing there. So then we check 5, nothing there. 6, nothing there. Then 7, nothing there. So then we're done. Okay. So that is for BFS. We see we have 1, 2, 3, 4, 5, 6, 7. Now DFS is on a tree. On trees, there's different types of DFS. There's in order, pre-order, and post-order. But pre-order is basically the same thing that we were going over before. So we're going to stick to pre-order. Pre-order is where you start at the root and you visit it. So DFS, start at the root and visit it. Then we visit the leftmost adjacent child, so 2. And then from there, we visit that leftmost adjacent child. We're going as deep as we can. Now 4 has no leftmost, so then we check its rightmost. Nothing there. So then we go back to 2, and we check its rightmost. It's a 5. So 5. That has no leftmost and has no rightmost. So we go back to 2, and we have visited all the adjacent ones. So we go back to 1, and we check 1's right. That's 3. So we 3. Once we hit 3, we're going to check its leftmost. That's 6. So 6. But that has no left and has no right. So we're going to backtrack back to 3 and go to that right. That is a 7. So 7. We're going to check 7's left and rightmost. Nothing there. So then we're going to backtrack back to 3. And then that means that left and right have been checked already. So we backtrack to 1. And if we appear back at the root, that means we're done. So that is DFS. So we see here, we went to 1, to 2, to 4, to 5, to 3, to 6, to 7. And that's that. Okay, does that make sense? Okay. Now let's try with a harder graph. Right here. Actually, let me just copy it down here. Oh shit, wrong one. I think someone's mic is unmuted. All right. So now we're going to try doing BFS on this, and we know that BFS is done with a Q. It's done with a Q because, let's say we go here, we do first come, first serve, where this is 1, then we check 2, 4, 5. Since 2 became 4 and 5, we do 2 first, then do 7, 6, 3, and so on. Okay. So I'm going to draw the cue like this. Usually it's drawn from right to left, but I'm going to do it from left to right. Okay, and then remember, you can start at any starting vertex. I'm just going to start at 1 because it's the lowest. And yeah. So I'm going to put our output right there. And we're going to start at 1. Okay. Since we're starting at 1, we can obviously put 1 right here, and that's going to be on the cue. Once 1 is on the cue, we're going to pop it from the cue, or remove it from the cue, and then we're going to put its adjacent vertexes onto the cue. So let's go ahead and put 2 and 4, and 2 and 4. Okay. So now we have 2 and 4. Then we're going to pop off the next part of the cue, which would be 2, because that came first. And we're going to go ahead and visit 5, 7, and 8. So we can put 5, 7, 8. 5, 7, 8. Once we do that, we're going to pop off the next, which is 4. 4 visits 3. So 3, 3. And I gotta open this up. And once we're at that point there, we go ahead and pop 5. With 5, we see that 5 was already visited. So, sorry, what 5 is adjacent to is 2, 7, 8, and 6. 2, 7, 8, and 6 were already visited here, here, and here, except for 6, sorry, so 6 has not been visited. So we can go ahead and visit 6. And 6 goes right there. Okay. Once we're at...
So does order matter? Like, you put a 1 first and 2, 4, right? Can you put like 1, 4, 2?
Yeah, you can. The order doesn't matter, but the order that you visit them doesn't matter, but the order that you visit the children matter, because let's say I did 1, 4, 2, then I would have to visit 4 next, not 2.
Yeah.
So I would do 1, 4, 2. Then after that, I would have to go to the 3 and not the 5, 8, and 5, 7, and 8.
Oh, okay. Thank you.
No problem. So now we're finished with the 5. So we're gonna pop off this 7 and see what it's adjacent to. That was adjacent to 5 and 8 and 2, but those are already visited, so we can go to the next one. 8, we're gonna pop and see what is that adjacent to. 2 and 7, that has already been visited, so we can ignore that. Now we're going to pop 3. 3 is adjacent to 10 and 9, so I'm just going to 10 and 9, and I'm going to put 10, 9 there. And then we can continue with 6. 6, it's only adjacent to 5, and 5 has already been visited, so we can continue. 10, it's only adjacent to 3. 3 has already been visited, so we can just pop that. And then 9, we're going to pop and check what it's visited. Sorry, what it's adjacent to. Only adjacent to 3, and that's already been visited, so that's basically it. And then once the queue is empty, then we just stop it, so we can just break. That's just a little pseudocode, but yeah. And this will be a valid BFS. If you want to check out another one, here's another one right here. Right, we're here. we went from 1, but then went to 4 and 2, which is what Olivia was saying. Go from 1 to 4 to 2. After doing that, we have to go to 3, which is right here. Okay. After visiting 3, then we go back to this 2 and add 5, 7, 8. So that's 5, 7, 8. Okay. After visiting the 2, we visit back to the 3, so we put 10 and 9. Okay. And then after doing that, then we go to the 5. 5 is just adjacent to 6. That's not been visited, so 6 goes there. And then 7, 8, 9, 10 have already been visited. So we just pop those off. Once we get to 6, we see that 5 already visited, so we just pop that. That's good. All right. Another valid one. Let's think of what if we did the starting vertex at 6? So I'm going to put Q like so. And our output looks like this. So 6. The only thing that's adjacent to 6 is 5. Well, I'm going to pop it, then look at what's adjacent, which is 5. So we put 5 right here, and then we also put it on the output. Then we're going to pop 5 and put what's adjacent onto it. So 2, 7, 8, 2, 7, 8. Okay. Then we're going to pop the 2. We see 2 is adjacent to 7 and 8, but those have already been visited. But it's also adjacent to 1 and 3. So we're going to put 1, 3, 1, 3. Then we're going to pop 7 and see what it's adjacent to. It's adjacent to 5 and 8 and 2. Those have already been visited, so we can skip that. Then we're going to pop 8. 8 is adjacent to 2, 7, and 5. Those have already been visited, so we can continue. Then we're going to pop 1. 1 is adjacent to 2 and 4. 2 has already been visited, but 4 hasn't. So we're going to put 4, 4. Then we're going to pop 3. 3 is adjacent to 4, 2, 10, and 9, but 4 and 2 have already been visited. So we're going to visit 10 and 9. So 10, 9. Then we're going to pop 4. 4 is adjacent to 1 and 3. Those have already been visited. I forgot to put 10 and 9. Okay, we were going to pop 10. 1 and 3 have already been visited, so we continue. So we're going to pop 10. 10 is only adjacent to 3. That's already been visited, so we continue. 9. 9 is only adjacent to 3, and that's already been visited, so we are going to continue, but nothing else is on the queue, so we stop. And then we are left with 6, 5, 2, 7, 8, 1, 3, 4, 10, 9. Okay. And that is another valid BFS. Okay. And anytime you run BFS on a tree, you also get a valid spanning tree. So let's say I had this as the root, Let's say that connected to 5. And then from there, we say that that 5 connected to 2, 7, and 8. So we had it like this. 2, 7, and 8. And then from there, we had 2 connect to 1 and 3. Okay. Which it's easier to do this if you are actually writing it out while you're doing it. But 1 would connect to 4, and then 3 would connect to 9 and 10. Okay. All right. So that is BFS on a graph. Is there any questions about that before we move on to DFS? No questions. All right. So now we're going to do DFS. And with DFS, this one is a bit harder. With DFS, we implement it with a stack. Okay. So what the stack does is let's say we have this stack. Looks like that. And what it does is that we are going to start at some vertex. Let's call it 1. And we're going to visit one of its adjacent vertexes. When we visit one of the adjacent vertexes, the original one we were at, that's going to go onto the stack. Because at some point we want to go backwards from the 1 so we can get to 2. Okay. So let's say we were at 1 and then we go to 4. And this is going to be our output. Sorry, I forgot to write it. So right now we're at 1, then we're at 4. Okay. We see that 4 is adjacent to 3. So we're going to put 4 onto our stack and write a 3. From there we see that 3 is adjacent to 10 and 9 and 2. So we're going to put 3 onto the stack and visit 10. From there, we see that 10 has no children, so we're going to backtrack back to the top of the stack. So whatever is there is going to be popped. So I will just do this. You'll see that it gets kind of annoying. It's going to be popped. Once we're popped, we're going to look at what was the next adjacent vertex with that popped vertex. That was 10. So we're going to put this back onto the stack and put, sorry, not 10, it was 9. That was 9. Once we get to 9, we see there's no other adjacent vertexes that it gets connected to. So 3 gets popped again. And then we look like this. Okay. Once we're back at 3, because we popped it off, we see what's the next vertex? 2. So we're going to put 3 back onto the stack and then visit 2. Once we're at 2, we have to choose a vertex that we want to go to next. So let me just move this over. Oh, I think I might move everything. Okay. 2 we see connects to 1, 5, 7, and 8. I'm just going to go with the 1. So we're going to put 2 onto the stack and then write 1. Once we're at 1, we see that we are connected to vertices that were already visited, right? So we are going to again go backwards and backtrack back to the 2. So now we are looking at 1, 4, 3, and 2 has been popped. And now we're looking at 5, 7, and 8. So I'm going to go to the 8, because why not? And to do that, we have to stall the 2. So we're going to put the 2 back onto the stack. And then we're going to put an 8 here. Once we're on the 8, we see that it is adjacent to 2, 5, and 7. Obviously, we're not going to go to 2 because that was already visited. So we're going to go to 5 or 7. I see the easiest to do is 7. So I'm just going to do 7. So we're going to stall the 8. And we're just going to put a 7. Once we're at 7, we see that it is adjacent to 2, 8, and 5. 2 and 8 have already been visited, so we're going to go to 5. So we're going to stall the 7. That becomes 5 right there. And then once we're at 5, we see we are adjacent to 2, 7, and 8, and also 6. 2, 8, and 7 have already been visited, so we are just going to visit 6 by stalling the 5. Then we're going to visit 6 by putting that like that. Once we're at 6, we see that there's nothing else it's adjacent to, so we're going to go backwards by popping the top of the stack. I don't want to write this multiple times, so I'm just going to put like an X like that. Once we're at 5, we see that 5, what it's adjacent to, is already been visited, so we're just going to pop the next portion, that is 7. Sorry, not portion. And we're going to see what is 7 adjacent to. 2, 5, and 8, that has already been visited, so we are going to pop the top of the stack again and get 8. What is 8 adjacent to? 2, 5, and 7. Why did I put 1 twice? Oh, sorry, I didn't mean to do that. My fault. There we go. Alright. Once we're at 8, we want to see what it has been, what is adjacent to. 2, 5, and 7. All those have already been visited, so we're going to pop the next part of the stack. That's 2. 2 is adjacent to 5, 7, 8, 1, and 3. Those have already been visited, so we pop the next part, which is the 3. 3 is adjacent to 4, 2, 10, and 9. Those are already visited, so we're going to pop the next part of the stack, 4. 4 is adjacent to 3 and 1. Those have already been visited, so now we're going to pop the next part, which is 1. 1 is adjacent to 4 and 2. Those have already been visited, so then we are done. So then once the stack is empty, just stop. Okay. And that is DFS on a graph with a stack. And we have another example up here as well, where we start at 1. So we go to 1. Okay. From 1, actually, is this the same one? 1, 4, 3, 10, 9, 2, 8, 7, 5. Okay. Well, it looks like I did the same exact route here. I don't know why I did that. Let's do another one. We can do 1 to 2. Instead of 4, we can go to 2. So let's say we go to 1 to 2. I'll write it out here. Let's say we do 1 to 2. From 2, we can go to, let's say 8. From 8, we can go to 7. From 7, we can go to 5. And from 5, we can go to 6. Then we backtrack. So from 6, we have to go backwards to here. 5, it's adjacent to 2, 7, and 8, but those have been visited. So we backtrack again to 7. 7 is adjacent to 2, 5, and 8. Those have been visited, so we're going to go backtrack to 8. 8 is adjacent to 2, 5, and 7. Those have already been visited, so we go to 2. And with 2, what we visited was 8, right? What it's still adjacent to is 5, 7, and 3. 5 and 7 have already been visited, so we're going to visit 3. So 3 goes there. And on 3, we can visit 9, 10, or 4. So I'm just going to go with the 9. 9 has nothing else adjacent to it, so we're going to backtrack to the 3. And let's just go with the 10. 10. Nothing else adjacent to the 10, so we're just going to backtrack and go back to the 3. And the last thing that's adjacent to the 3 is the 4, so we can go to the 4. To the 4. We see that what 4 is connected to, they've both been visited already, so we're going to backtrack to the 3. Once we're here, everything has been visited by the 3, so we're going to backtrack to the 2. And once we're at the 2, everything has been visited by the 2, so we backtrack to the 1. once we're back here at our starting vertex, that means that we are done. So this is another valid DFS, or depth first search. Okay. Does that make sense? Make sense? Okay. Just give me 1 second. All right. So, that is, what is the runtime? I'm pretty sure that BFS is. I think with BFS you don't have to do any backtracking, so for that it may be OVN, but let's check it really quickly. Where was it? Was it in here? I don't even remember. Oh yeah, because we're dealing with vertices and edges. Oh, there he is. Somewhere in here. Okay, it's just not here. Let me check in here. Okay, yeah, that's what we did with the stacks and the queues. If you want, this is the example we actually did in class. Let's just run through this really quickly. Breadth first search would be 1, 4. From that 1, we would go 2. From that 4, we would go 5. And then from that 2, we can just go 3. So valid breadth first search would be 0, 1, 4, 2, 5, 3. And then for DFS, that would be 0, 1, 2, 3, 5, 4. I think. Trying to understand what I even did here. I don't fucking remember. But anyways, let me see if the runtime's here. Okay, right here. So DFS is O of V plus E. Right? And let's try to understand why. So the reason for his code is because he first makes an array containing negative ones, and that represents the vertices. And then here, with the stack, he is traversing all of the edges. So again, here we have this creating an array of size V, okay? And then here we are traversing all the edges, so that is O of V plus E. And then BFS, did we even do that? I don't think we did. Does anyone have the runtime for BFS? Shouldn't it just be O of V? I don't remember. One, all right. Let me try looking it up. Oh, it's also O of V plus C. Huh. And then let me see DFS. But DFS just says O of N. Okay, that's weird. Then here says O of V plus E. Oh, you're saying V plus E, if E is greater than V, then E. But what if V is... Oh, okay. Okay, here's an explanation. Okay. So it says E is the set of all edges, so cardinality of E is the count of all edges in the graph. This alone should be enough to convince you that overall complexity can't be cardinality of E times cardinality of E, since we are not iterating over all the edges in the graph for each vertex. Gotcha. And then it says in the adjacency list representation, for each vertex V, we only traverse those nodes which are adjacent to it. The V factor of the V plus E seems to come from the number of Q operations done. Note that the complexity of the algorithm depends on the data structure used. Okay, I'm just going to go with both of them are O of V plus E, but if the number of edges is greater than the number of vertices, then it's O of E. And that should be true for both BFS and DFS. Yeah. There we go. Both DFS and BFS have an overall complexity of O of V plus E, with V being the number of vertices and E the number of edges in the graph. Okay, so I'm going to screenshot that. All right, and then I'm going to put that here. And then I'm also going to say if okay. All right, so that is the time complexity. Is everyone good now with BFS and DFS, or do I need to elaborate on anything? Oh. Okay. So now let's move on to the next graph algorithm, which is Prim's algorithm. Okay. What would be different applications for each? I think he said it. We were answering one of the questions for the homeworks. Oh wait, I'm on the wrong thing here. Yeah, that the Abdubar video is good too. I literally just used the same graph that he did. Okay, let me just paste this here.
This is recorded, right?
No. Okay, let me see. I think we said it here before.
For one of the exam questions, like for number 1 on the on the document, they give like something that was given in the quizzes. there a possibility that that could have been a thing?
Sorry, what?
Like, okay, I'm gonna hold on. Let me. Okay, I'm posting this in like the general in the general open chat. Like, there's a question like this on the final exam.
This is just insertion sort.
Yeah, no, but like he's asking like to display the algorithm.
Yeah.
Show what the array looks like after each iteration. Outer loop.
I don't understand what's your question.
Okay, can you like explain how? Okay, can you explain how he would want this to look if he were to give this question? Because it looks like it's a quiz question.
That's
It's
that's
exactly
his
a
that's
quick
his
question.
answer. Yeah, that's his answer right there.
Oh, that's the answer. Oh, okay. Okay. Gotcha. Sorry, my fault.
You're good. Right. So for applications, 8:30 a.m. is kind of early, but I guess. Yeah. I don't. Are you talking about like real world applications, Lauren, or what?
Yeah, like I think that he said that we would probably like be given like a scenario and then like he would ask us like make an algorithm based on this scenario. I guess like how would we know like whether to use like BFS versus DFS?
Well, first you have to, given the scenario, you have to think: is it weighted, unweighted? Of course, if it's unweighted, we'd be using BFS or DFS, but if it's weighted, then we would have to use Dijkstra's or Prim's. But in terms of choosing BFS or DFS, I think if the question asks something like, you're visiting every single vertex in order, then that'd be something like BFS. But for DFS, I'm not entirely sure. If you want, how about this? I just got an idea. I just had a great idea. Let's go to. Okay. Okay, so I'm going to copy this. And I'm going to tell ChatGPT, give me questions like this, but only questions involving BFS and DFS. What the fuck?
They better lock you up.
Okay, there we go. Okay. So I'm going to paste this here. Actually, let me make a new chat. And I am going to say, give me questions like these, but only for DFS and BFS. Okay. So this should be good practice. Then we'll move on to Prims and Dijkstra's. Okay, the shit is saying the answer. How do I stop? Okay, whatever.
You can just press the pause button on in the text box.
Oh.
See that square? Yeah.
Okay. Anyways, let me just see what it said. It said, hold on, someone emailed me. Okay. So here it said, exploring cultural reasons. So it says, given a world map graph where each country is a vertex and land borders are edges, use DFS to identify a region where all countries share a common cultural heritage. Huh. Okay, that I don't really understand. Detecting cycles in international relations in a graph representing international alliances. Countries are vertices and alliances are edges. Apply DFS to determine if there's a cycle of alliances. A group of countries where each is allied with the next. Okay, yeah. I don't even know what the fuck this is talking about. What does it at least say for BFS? Assuming you have to plan a journey to attend an international summit in the world map graph using BFS, find the shortest path. So I think for shortest paths with unweighted edges, best is BFS because you're starting from the root vertex and then you're visiting every other vertex, right? So if we're talking shortest path with unweighted edges, that is BFS. If we're talking shortest path with weighted edges, that is Dijkstra's algorithm. Okay. It didn't really give good examples though. Let me just paste the same exact question Lauren asked. So yeah, let me see. What would DFS be good for versus BFS? Okay. Let's see what it says. So it says for DFS, it explores as far as possible along each branch before backtracking. Okay, this isn't really giving me anything concrete. Okay, ideal use cases. Finding connected components. DFS is effective in exploring and marking all vertices in a connected component of a graph. Meaning it's good at finding what vertices are connected to other vertices. And then here, topological sorting. I don't know what the fuck that is, so we're gonna skip that. Cycle detection. So DFS can be used to detect cycles in a graph, which is crucial in applications like deadlock detection. Okay, so if he gives a question saying, how can we test or how can we detect if a graph has a cycle, or form an algorithm to find if there is a cycle in this graph, you can run DFS, and if you end up at the same vertex with DFS, then I believe that there is a graph. A cycle. And then this one says solving puzzles with only one solution. I don't think we need to know that. Okay. And then for BFS, it says BFS is ideal for finding the shortest path on unweighted edges. Again, that's what I said before. If it asks to find the shortest path on unweighted graphs, you use BFS because it guarantees the shortest path from the starting node to all nodes reached. Level order, yeah. BFS is useful in determining whether a graph is bipartite or not, whether it can be divided into two sets. Okay. And then social network applications, for example, find the degree of separation between two individuals. Oh, okay. So basically what this is saying, I don't know if he talked about degree of separation before. There's also degree of Kevin Bacon separations or whatever the fuck it's called. That would be a good implementation for BFS as well, because you're finding the shortest path to every other vertex in an unweighted graph. All right, so here are the key differences. For path findings, DFS can get stuck in long paths or loops, whereas BFS will find the shortest path, so that's a good one. Memory efficiency, okay, we don't have to know that. Completeness, DFS is generally complete, meaning it will find a solution if one exists. DFS can be incomplete in infinite graphs. Yeah, that didn't really give much. I'm gonna be honest. I guess honestly, just for BFS, if it's unweighted and you have to find the shortest path, use BFS. If it's weighted and you have to find the shortest path, then you're going to be using what's it called? You're going to be using Dijkstra's. All right. Okay, so now let's look at Prim's algorithm. So DFS is good for finding one solution path? I believe so, yeah. So let's start off with Prims. I'm just gonna write a bunch of vertices, vertices. Okay. And we're just going to give these some random numbers. So 2, 4, 3, 1, 5, 2, 3, 7, 2, 1, 5, 3. Did I miss anything? I don't think so, right? Okay. So again, with shortest path, not least way, right? Yeah, shortest path. That is for BFS. Because it connects the root to every other vertex. Okay. So here, I'm gonna go like that. We can start at any vertex we want. I'm just gonna start at 0. And what Prim's algorithm is doing is that we're making a minimum spanning tree. Okay, so basically we're going from graph to tree. So, I am going to first start at 0 and write its candidate edges. So 2, 1, 3, and 4. Which algorithm is good for undirected graphs to determine whether the graph is a tree? Whether the graph is a tree? Sorry?
You're doing Prim's algorithm?
Yeah, this is Prim's algorithm. I'm just answering Spimy's question. I mean, to be a tree, it just can't have any cycles. And for detecting a cycle, DFS is good. So maybe DFS? If you want, we can check that out first. But that's just my assumption. Which algorithm is good for undirected graph to determine whether that graph is a tree? So let's see. Oh, it says both of them, but I set that for search. The key properties to check whether an undirected graph is a tree. Connectivity, all vertices must be connected. And it says the graph must not contain any cycles. And then this is how you do it. So it says you start at any vertex and you track visited vertexes. So check for cycles. If you visit a vertex that's already been visited, and it's not a direct parent of a current vertex, a cycle is a parent. Is present. Meaning, if we visit some vertex, right, and what it's adjacent to If that's already been visited and it's not a parent of whatever vertex we're looking at, then that means that there is a cycle. And that can be done with either BFS or DFS. Okay. So that is answer to that question. And then to ensure, we also, to be a tree, all vertices must be connected to the overall tree. So you also have to look at each vertex and make sure that they are all been visited. If there's still like one or two that, or any, if there's at least one that hasn't been visited, then it's not a tree. Okay. Yep, no problem. All right, so let's finish this question up. After we do Dijksha's, we're going to take a quick break because I have to feed my pets. They're scratching at my door, waiting to be fed. And then after that, we are going to do one of the past exams. So with Prim's algorithm, we basically want to go on the edge that has less weight. So right here, it is 1 with a weight of 2. So we're going to go boom, 2, 1. And let's bring our 3 back with a 7. Let's bring our 4 back with a 4 and a 3. And then we have to see, what is 1 connected to? Well, 1 has candidate edges to 2 with a 3. It also has an edge to 5 with a 4. And then it also has an edge to 4. But we see that 0 already has a candidate edge to 4. But the one from 1 to 4 has less weight than the one from 0 to 3. So from 0 to 4, so we're going to replace that. So actually, let me just shift it over so it looks better. With a 1. Okay, does that make sense? Yes, no, maybe. I'll take that as a yes. Okay, so now we're looking like that. And then now we're going to go to the one that has the least weight again. Right now, that would be 4, right? Because 4 has a weight of 1. So we're going to go to 4. It's going to look like this. 0, 1, 4. It's a 1. I think that's a 2. We're going to put back all of our previous. So that had a 7. 1 was connected to 4 that way, and then 1 was connected to 3 that way. Okay, and then now we must see what was 4 connected to. We see 4 is connected to 0, but that has already been visited, and it's also connected to 6 with a weight of 3. Okay, and then it's also connected to 3, and it's also connected to 5. To 3, we see we have a lesser weight because from 0 to 3 it was 7, but from 4 to 3 it was 2. So we can put a 2 here and get rid of this candidate edge. And then from 4 to 5, we see the weight was 5, but the current edge to 5 is 4, which is lesser, so we're not going to change it. Okay. And then this is our current thing that we're looking at here. Okay. All right. And then from here, the next smallest would be from 4 to 3. So Okay. And once we're at 3, we have to see what is that adjacent to. Well, 3 is adjacent to 0, but that has already been visited. And we see that 3 is also adjacent to 6, but that hasn't been visited. It's an adjacent, is a candidate edge to 6. And we see the edge from 3 to 6 is 2, but the current edge from 4 to 6 is 3. 2 is less than 3, so we're going to replace that with our 2. And we see that should be the only thing that gets replaced. Okay. Then from here, the lesser one again is 2. So I'm just going to write it here. 0, 1. Oh, sorry. That wasn't fitted yet. 2 with a 3. 2. 4. Okay. So now this is what we're looking at. And we have to see what is 6 connected to. Well, 6 is connected to 4, but 4 has already been visited, so we don't have to worry about that. And 6 is connected to 3, that was already visited, so we don't have to worry about that. Only thing it's connected to is 5, and we have to worry about that because it's connected with a weight of 1. And the current candidate edge is connected with a weight of 4. That's less than, so we're going to replace that and delete this one. So now this is what we're looking at. From here, obviously 1 is the lesser, so we are just going to, let me just copy this. Okay. 1 is the lesser, so we are going to go ahead and write that. Okay. And then once we're at 5, we have to see what is adjacent to 5. Well, obviously 6 is adjacent to 5, but that has been visited. 4 is adjacent to 5, but that has been visited. And 2 is adjacent to 5, but that hasn't. Oh, sorry. 1 is adjacent to 5, that's already been visited. 2 is adjacent to 5, but that hasn't been visited. And it has a weight of 5. The current adjacency, candidate edge is connected to 3 with a weight of, connected to 2 with a weight of 3. But this one is connected to 2 with a weight of 5. So we don't want to replace it, and we want to keep this one. Once we keep this one, this is the last one remaining. So we can just go ahead and fill it in. So I'm going to go like that. Copy that. Go over here. Paste it. And it becomes like this. Put 3. Okay. And that is our minimum spanning tree. So if we write this as a tree now, it's going to look something like this. 0 to 1. 1 connects to 4 and 2. So I'll just put a 2 here and a 4 here. 4 connects to 3. 3 connects to 6. And 6 connects to 5. Keep in mind, it's not a minimum binary search tree, it's just a minimum tree. And it comes up with this. Okay. And we can calculate the sum of the weights. So that's 2 plus 3. That's, oh, wait, we're missing a weight here. That's 1. So 2 plus 3, that's 5, plus 1, that's 6, 7, 8, 9, 10, 11. So starting from here, it would only take 11, it would only cost 11 steps to visit each vertex, right? Because this would be 2, 3, 1, 2, 2, 1. Okay. And that is Prim's algorithm. Are there any questions about that one? Runtime. Let's go ahead and check. Not sure if you went over the runtime. I don't think we discussed the. Oh, right here. V squared. This is the actual code for Prim's algorithm. We need an array for visited, array for weight, an array for prev. Right here, I can just go over each part. This one is for the size of the vertices. So this part here is O of V. Okay. Then over here, we are running, again, this part here for the size of the vertexes. It's O of V. And here, we are writing this portion here for the number of edges. So that is O of E. And then this part here is, again, for the number of vertexes. That's O of V. So then it comes out to O of V times V plus E. Which that becomes O of V squared plus E times V, which we know V would be bigger. So this is O of V squared. You discussed how it could also be E log V if we used a min heap. That may be good to remember. Min heap for if we didn't use 3 arrays, just use a min heap.
I mean, well, the idea for prims and textures, we have to find the minimum every time, right? So using a min heap, we can do that easily. And that also makes it easy to change the weights when we're considering candidate edges because of decrease key in that function. So in that case, it would be a good implementation.
So then, if we use a min heap O of E log V. Okay. But just remember the base for, I think, Dijkstra's and Prims, I believe, is O of V squared. Okay. All right, and then I'll just rewrite it here. O of V squared. All right. Whew. Are there any other questions about that?
Show us the code again, just so we can see. Thank you.
You want me to take a picture of it?
There, posted it.
All right. Of course, this is code that you don't have to memorize because only code you have to do on the exam is hash maps. What?
Hash maps is the required one, but what about the algorithm? How much would we have to code the entire thing?
Well, that's only for extra credit. It's not required.
complexity is not.
All right.
Honestly, the easiest one would be the data structures question.
I mean, it depends.
He's giving us 5 types, though. He said he's giving us the what's it called? Queue, stack, party queue, AVL tree, and hash tables.
He said those were going to be the 3?
Those were going to be the 5, yeah.
That's right. Why did I say 3? 5. Okay.
He said
So, yeah, so that question should be easy. Is there any code for BFS and DFS?
he didn't do it in class, I think.
I can show you
Either
my
that or
code
vice
for it.
versa. What's the potential for number 5, though? That's the biggest thing in my mind.
Oh yeah, we also, so this is we forgot to go over this as well. The time and space complexity for adjacency list and adjacency matrix. Space complexity for adjacency matrix is obviously O of V squared. And then for adjacency list, you have a slot for each vertex, and each vertex must contain each edge. So that is O of V plus E. Adding a vertex to adjacent matrix, that's just O of V squared. When adjacent list, that's done in O of 1 time. Adding an edge is just for both of those O of 1. Removing an edge, adjacent matrix O of 1, but adjacency list, it's O of E. Because again, it's a list of edges, and if you have to remove one, you have to shift them all over in the worst case. So that's O of E. Then removing a vertex, you have to create an entire copy for the JC matrix, but leave out one row and one column. So that is O of V squared. And then removing a vertex for JC list, it's O of V plus E, because you have to first remove the vertex and then go to each you have to visit each vertex that is adjacent to and remove that from its edges. And again, removing an edge is O of V. So you potentially have to, in the worst case, visit each V minus 1 vertex and then remove the vertex from each of those edges for each of those lists. And let me find the code that I did for and don't be shocked by this. This is just for the Udemy course. You don't have to know this for the exam. Okay, right here. So this was the code that I did for BFS, where you just start off with an array list that's containing everything you are traversing. In a queue, remember with a queue, you can't just say equals new queue. You have to say equals new. You could just say linked list if you want. And then from there, you just add the first node. And while the queue.size is greater than 0, you go ahead and remove what's at the current queue. Okay. And then you add it to results. And if there's something to the left of it, add it to the queue. And if there's something to the right of it, add that to the queue. And at the end, just return the list. So BFS, the code for that is very easy. And I don't think I did DFS code. Oh, I think I did. Oh, I did. So DFS code, I did this without a stack. I just did it recursively, which recursively is actually easier to do than with a stack. So I'd actually, if he makes you do this for like the mystery question or something, this is better. It's just easier to do recursively. So yeah. And he did give the code for that as well. Let me see if it's here. Where was it? Was it on trees? I don't remember. Remember him going over it. Does anyone have that code? I remember him doing it. Oh, here we go. So this is his breadth first search code. But here he's not doing anything with the traversal. He's just kind of traversing it and not doing anything. Where he's adding it to the queue, then when he finds it, he dequeues it, and so on. He's printing it. I didn't see that part. So yeah, this is his breadth first code. Pretty easy. If you want, you can screenshot this. But that is the code for breadth first. Again, not hard. And for the DQ part, oh wait, I just realized I put new queue. I think he didn't mean to do that. That is illegal. You can't do that. Link list. Because Q is an abstract class, so you can't instantiate an abstract class. So that wouldn't be valid. Okay, middle and pre, it's before everything. Does that make sense? Okay, I hope that makes sense. All right, and then of course the post order looks like this. Right, where post order, what it does is it goes leftmost. Once it's at the leftmost, it prints, then it goes upwards, skips its root, then goes to the right. If there's nothing to right, then it prints the root. Right, so we're going to start at 1, go down to 2, there's something to the left, so go down to 4, nothing to left or right, so we're going to print 4. Once we're at 4, nothing to left or right, so we're going to go back and go to the right, that's 5. Boom, nothing to the left or right, so we go back here. Once we're back here, we hit the 2. Then we go here, we're not going to go and hit the root yet, we're going to go downwards to the 3, but then go down to the left, that is 6. Then some of these are right here, so 7, 3, 1. So that is post order. And I'm getting a call. Give me 1 second. Alright, sorry about that. So that is the code for breadth first search and depth first search. Are there any questions concerning any of those topics?
Yeah, so I know we did this like with trees, like the binary tree nodes and stuff. Does it matter? Like, can we use this code also like for graphs and stuff? For breadth first and depth first?
I don't think so, because this only correlates to binary tree nodes where there's just a left child and a right child. For graphs, that you would have to do with a stack. But for trees, you can do it with a stack or recursively.
Okay, do you happen to have the code for the stack version of it?
I don't think he did that in class. Let me check.
He didn't give a code for what was it, stacks? I don't think he did.
Yeah, I don't think he did. If he didn't give it, then he doesn't expect you to know it.
I mean, I guess that's true. Yeah.
Oh wait, it's right here, I think. Wait,
Wait, really?
yeah, this
Oh,
is
I
it
took
right here.
pictures of his stuff. How did I miss this?
So here, this way, so that he does a stack where he has an array to hold the previous vertices, and then a stack where we push the first element. With a graph, we're just going to be using pre-order traversal. We're not going to be worrying about in-order, post-order, just pre-order, okay? Because pre-order is the closest to the definition of depth first search. And then we're just going to push the first vertex. Sorry, the first element. I don't know why it says push 0. that should be push adjacency dot get 0, I think, something like that. But and then once we're in there, we're gonna pop the top of the stack and see if there's anything adjacent to it. If there is, then we're going to say if the previous vertexes, if they're equal to -1, then set them equal to whatever that current vertex is, and then push it to the top of the stack. Once we've done that, then it goes all the way to the top, and then it does that again with the last item pushed to the top, pushed to the top of the stack. And yeah, honestly, you don't have to remember this stuff. I don't think you shouldn't have to. I don't think he expects you to memorize this entire thing. But yeah. Who is messaging me? Okay, I don't know who that is. All right. Any questions about that? Or is Lauren, is this what you were looking for?
Yeah, I know that he said like for the extra credit part, you have to code the algorithm. So I'm
Yeah,
assuming like this is what you're talking about.
Yeah, I'm guessing that it's you're making your own algorithm again, so it's like saying, given a graph, find if there is a cycle. Honestly, I'd that's why it's extra credit. I don't think he expects any of us to code that. So if you want to do that, you can, but obviously the answer to the question is not just going to be like, oh yeah, do DFS. You're designing your own algorithm, so yeah.
I guess would you have any like suggestions on like how to prepare for that, I guess? Or like is it even worth it to even like do that part
Prepare
again?
for the code or prepare for the question itself?
I guess both parts.
I was just wondering if you gave. So for the question itself, I would recommend memorizing all the definitions of graphs and trees. Like he could give a question saying, would this graph be balanced, or would this graph be, does this graph have a cycle? You need to be able to know what that is, and then explain an algorithm to find if that is true, right? I myself, I don't have all that things memorized. I'm just gonna memorize that after we do this. I think I have some of those definitions here. Actually, give me a second. I do not. Maybe in the Udemy. Hold on. Come on. Okay, yeah, I don't have those definitions. But again, I would recommend trying to memorize that. Did he give those definitions? I don't even see that he did. But I feel like he should have. Or am I blind? I don't know. Yeah, I do not know. Okay. But after this call, I'm going to make a Quizlet. The Quizlet will contain definitions to remember and also runtimes to remember. So it's going to say, what is the best, what is like the average case of insertion sort? You should know that that is n squared. What is the best case of bubble sort? You should know that's n. What is the worst case of quick sort? You should know that's n squared. Things like that. And also insertion sort. What is the best case for insertion sort? You should know that's also n. Okay. Yeah, so I'll make that after this call. And you guys can just use that. And I'll also add definitions like what is a complete graph? What is a balanced graph? things like that. So, unless I think he might have defined it in the trees section. Let me see. Give me 1 second. Okay. So yeah, he defined leaves, depth, height, which people define depth and height a bit differently. He defines it as depth, the level that it's at, and height, the level that it's at going upwards. So height for A would be 1, 2. That's the height, but the depth is 1 because it's at level 1. B, the height would be 1. E, the height would be 0 because it's all the way at the bottom, but the depth would be 1, 2. Okay, so that's a good definition to remember again. Did he give any other definitions? Of course, obviously know the definition of a binary tree. And also know the difference between a binary tree and a binary search tree. Yes, a binary search tree is a binary tree, but there's differences between a binary tree and a binary search tree. So please remember that as well.
Binary tree has 2 children nodes, but that's about it. A binary search tree is a binary tree, but sorted from least to greatest, I believe, right? Kind of like an AVL tree.
Well, the binary tree can have at most 2 children. It's not always going to have 2 children. So it can have 1 child. It can have 1 child. It can have 0 children, but it can't have 3.
Right, but
believe
binary
that-
tree applies the same definition, doesn't it?
No, I was saying that is the definition of binary tree.
Right, but binary search tree, they have like a specific, like it's between either 0 or 2 children for BST.
That's for both. The only difference between binary tree and binary search tree is is where the numbers are inserted.
Yeah,
Because there has to the lower numbers have to be to the left, and then the greater numbers have to be to the right. I'm saying
yeah,
what
like
you
an
said.
AVL tree.
I'm saying what you said for binary tree. You said that it has to have 2 children.
It has to have 0 to 2 children.
Yeah, 0 to 2. And then let me see if he gave any other definitions. What is this? Oh, this is proofs. Oh, I hate this one. Honestly, if he gives this one for the mystery question, if you can just memorize this part here, then you should be good. Where n is equal to f plus h plus l. This is one of the questions from the homework. And he said that this was on an exam before as well.
This man's a demon.
Yeah, it's just saying in a binary tree, a full node is a node with 2 children. Prove that the number of full nodes plus 1 is equal to the number of leaves in a non-empty binary tree. So if you take the number of nodes, that is equal to the number of full nodes plus the number of half nodes plus the number of leaf nodes. And then you kind of just have to do that math, and yeah. I don't even know, but whatever.
Wait, why is half? Wait, go back. Why is half? Why is the half node equal to 2f? Wait, what?
Because, wait, what? What? Sorry, I don't know what you mean.
You got n equals f plus h plus l, right? And then you got n equals 1 plus 2f plus h. Where did that come from?
I don't know, I just copied him. I don't know.
Oh no.
Yeah. But let me see if there's any other definitions here. I don't think so. It's just binary search trees. Oh, this is good to remember as well. Order of binary search tree. Worst case would be a really tall tree, so O of n. So the order to find a number in a binary search tree, that is O of n for the worst case. But I think the best and average case, I believe, is what, log n, right? Something like that. I don't know. Actually, no. That's if it's balanced. I don't remember. But yeah. Okay. Any other definitions here? I don't think so. Oh, this is one definition of balanced. For each node, the heights of the nodes left and right subtrees can differ by no more than 1. That's what balanced is. Okay. I think that's it. So I'll make the Quizlet after this. right now, let's just do Dijkstra's, then we'll take a break because I have to feed my animals and they are just waiting outside my door. All right. All right, Dijkstra's algorithm, we will use the same graph just to also show the difference between the two algorithms. All right. So with Dijkstra's algorithm, we can start at any node. We're just going to start at 0. And what it does is it finds shortest path what the fuck? Shortest path from one node to every other node. Okay. And the one node that we're talking about, it depends on what you're picking. So let's say we start the algorithm at vertex 2. We're going to be finding the shortest path from vertex 2 to every other node. Here we're starting with a vertex 0, so we're going to be finding the shortest path from vertex 0 to every other node. Okay. So if we're starting at 0, we have 3 candidate edges. And what we're going to do is we're going to have the first vertex. That's going to be there. 3 and 4. Boom and boom. And we're going to have the current weight connecting to them at this portion right here. Okay, so 1, that's going to be 2. To the 4, that is 3. And to the 3, that is 7. Okay. So this is what we're looking at now. All right. And we see that the shortest would be going from 0 to 1. So we're going to go from 0 to 1. And we're going to bring back our candidates. And we're going to see, what does 1 also connect to? Well, 1 connects to 2. And it also connects to 5. And we see that whatever weight is here, we have to add that with whatever weight it took to get to here. So we see that from 1 to 2 it's 3. But we see that we also have this portion here as 2. So it's going to be 5. Because 3 plus 2 is 5. And then from 1 to 5, we see that there is an edge with 4. So 4 plus 2 is 6. Right? And then finally, we also see that 1 connects to 4 with a weight of 1. Well, this is 2, and whatever's here would be 1, so that'd be 3. But we see that this is already 3, so it's not less than. So we can just keep it like that. Okay? Because it's the same thing. Now, our least expensive path would be from 0 to 4, so that's what we're going to do. I'm going to just copy this to make this faster so we can move on to the practice exam. Right here. And we're going to go to 4. So, boom. Oh, shit. And now we're at 4. And we're going to see what are the new things that we're connecting to. Well, 6 is the new one. Okay. And the path between 4 and 3, the path between 4 and 6 is 3. So it's going to be 3 plus whatever the current edge is. That's 3, so that's going to be 6. So 6, 6. Okay. What else does 4 connect to? We connect to 3 and we connect to 5. Okay. The connection between 4 and 3 is 2, and 2 plus 3 is 5. So now we're comparing it between 3, 5 and 3, 7. 3, 5 is obviously less, so we're going to do that instead. Like so. And now we have 3, 5. Okay. And then from there, we also connect to 5 with a weight of 5 right here. But we also have to add what we are originally working with as well. So it's 3 plus 5. Okay. And that is 8. But we see here, it's already weight of 6. 8 is greater than 6, so we're not going to replace that. Okay. So now this is what we're working with. Someone's calling me. So now this is what we're working with, right? So from here, we see that the least weight would be this one right here. So we're going to go to the 3. I'm going to copy this. Boom. We're going to go like that. And then we're going to not make it a dotted line. We're going to solidify it. So boom, boom. And then we're going to see what does 3 connect to. Well, the only new thing it connects to is 6 with a weight of 2. But it's 5 plus 2, which is 7. So the weight to here would be 7. And we see there's already a 6 there, so that's less than. So we're not going to change anything. Okay. Now this is what we're working with. We see that the least weight at this portion here is 5. So we're going to go to the 5. Like so. Copy that. Bring it over here. And now we have that. And this 2 connects to the 5 with a weight of 5. So that'd be 5 plus 5, that's 10 to 5. And obviously 10 is greater than 6, so we're not going to do that. And now we've got this. These have same weights, so we are just going to do the lesser one. This is 6, this is 5. So we're just going to go to the 5. You can go to either one, but I think the common practice is to go to the lesser weight. So let's go over here. Like so. I'm going to erase that. Go like that. And of course, 5 connects to 6 with a weight of 1. So that would be 6 plus 1, that's 7. 7 is greater than 1, so we're not going to replace. And we're just going to finish up this last portion here. So let's go ahead and copy that. And there we go. So this is the shortest path between vertex 0 and every other vertex, and we could see the difference between the two. When we finished it, we looked like this for Prim's algorithm, right? But for Dijkstra's, we have this, right? So it's something completely different. But the runtime for both of these is O of V squared. Okay. But if we use a heap, it is O of E log V. Okay. All right. Are there any questions about that?
Can you explain why it would be E log V with the heat?
Honestly, I don't even know. I just know that's why. But if we go here, I know why it's O of V squared, but I don't remember why he said it's E log V. Do you remember why, Chrysler, or no? Okay, Chrysler's gone, I think. All right. So, but yeah, I'm not entirely sure. I can look that up. I think he said an example with planar graph. Yeah, I'm not too sure. Oh, I guess. So we said that after doing Dijkstra's, we would take a break. So how about we take a break for like 15 minutes? Because I have to go feed my animals. And during the break, if someone can look up why that is why that's E log V, that'd be great, and then we could walk through the explanation of that. Right. So I will be back in 15 minutes. If y'all want to go, that's fine, but I'm just gonna stay muted here, and I will be back. All right. Yep. Okay. Online it says that the runtime for Dijkstra's is not V squared. Hold on, let me check the notes really quickly. Graphs should still be V squared. Because the only thing we change is summing. Honestly, I would say just go with his code. And I would say that the runtime for both algorithms is V squared. And if you use a heap, it's O of E log V. Alright. So let me share my screen again. Right, so basically we've covered all the topics so far. Obviously we haven't covered every single topic in the class. We've just covered what's it called? We just covered the 4 questions, and we don't know what the mystery question is, so yeah. Anyways, I'm going to go ahead and open up the blank copy Rizwan sent. So thank you very much, Rizwan. And okay. And I'm gonna go all the way over here. I'm gonna bring it over here. So let's go ahead and do this question. All right. So, oh shit, we don't have space to do the question. Damn. Okay, it should be fine. Yeah, it should be fine. Okay. So first thing we're gonna do is insertion sort. I'm just gonna screenshot each individual questions so we can have room. Okay, and I'm going to bring it over here by doing this. And then that is going to go here. Okay. So it's saying perform insertion sort on the following array. So we have 5, 5, 2, 1, 3, 6, 4. Okay. And remember we said that with insertion sort, we assume that the first part is in the correct position. Okay, so this is what we're looking at right now. Something like this. And then we want to look at the next position and see where does this have to be inserted in the left array for this to be sorted. And that would be right here, 2, 5, then 1, 3, 6, 4. Then where does this 1 have to be inserted? Right here, 1, 2, 5. Then where does this 3 have to be inserted? 1, 2, 3, 5, 6, 4. Then where does the 6 have to be inserted? It doesn't have to be inserted anywhere. It can just stay where it's at. And then where does this 4 have to go? 1, 2, 3, 4, 5, 6. Okay? So that is the answer to this question. Are there any questions about that? All right, so let's check if this is correct. Where were the answers sent? In here, right? Okay. What just happened? My shit just broke. I don't know what's going on. I click done. Let's let that load first. There we go. Okay. So it's not letting me zoom in, so please just don't look at the answers below. But we see that we did 5, 2, 1, 3, 6, 4. Then we inserted the 2, then the 1, then the 3, then the 5, then the 4, and then the 6. But for some reason he didn't include the last iteration, so it just reads 1, 2, 3, 4. Oh no, sorry, he didn't. Sorry, I'm stupid. But yeah, that is correct. Oh, what just happened? All right. Any questions about that? I see someone's typing. Didn't he say he wasn't going to put quiz type questions on there though? I don't know. We're just looking at a past final, so this is on a past final. Okay. Give the worst case running time for quicksort and a short explanation of what causes that runtime. So this is a question 1 type of question. So this would be the answer, and I gave this answer yesterday. So hopefully you guys remember how to do it. So here, again, we're saying give the worst case running time for quicksort and short explanation of what causes that runtime. So for the worst case, we said that for quicksort, it's O of n squared, right? And then remember for the best and average, we said that it is O of n log n. Okay. So the reason that the worst case is n squared right? It says a short explanation of what causes that runtime. So we can say the worst case runtime. Oh, worst case runtime of quicksort is O of n squared. This is because if I think it's if bad pivots are chosen, it would cause us to loop over entire array to find next swap. And this is done n times. Thus, O of n squared. Now, I can't exactly pinpoint what he meant by bad pivots. He was simply just saying, like, hey, if we choose a bad pivot, it's going to cause O of n squared because we'd have to do more iterations or something. I don't even remember what it was. But that is why, in the worst case, it's O of n squared, but in the best and average, it's still n log n. And by best, I mean it's already sorted. It's still going to be n log n. Okay. So that is number 2. Does anyone have a better explanation than that? Or if anyone's able to find a better explanation online, please let me know and we will change that answer. But that's the best thing I could think of, or that's what I would have put. It's probably wrong though, but I just know O of n squared is correct. Yeah, you can be more specific with the bad pivots, but I honestly do not know what he meant by bad pivots. If we want, we can look it up. Let's see. The least value. Oh, gotcha. So if the chosen pivot is already the least value or the greatest value, then we would have to loop over the entire array to find whatever we're looking for. If we don't find it, then we would have to either leave the pivot there or swap it to the other position. And that would be n squared. So a bad pivot means least or greatest value in array. Okay. All right. Number 3. Suppose you have an array of n elements containing only 2 distinct keys, true and false. Explain or code an O of n algorithm to it's this question. To rearrange the list so all false elements precede all true elements. You may use only constant extra space, which means you cannot count the true or false elements. So for this question, you just have to explain. You don't have to code, which is good. So the explanation for this, I think would be, let me think. Actually, let me first screenshot this. There we go. Oh, I completely forgot. We have the answer for number 2. We could see what explanation he put. Let's check. Never mind. There's no answer there. Okay. Never mind. It's just it's the same exact question. But here we're not coding it. We are explaining it. You can code it if you wanted to, but here it's just asking to explain. So if we go here, let's see. It says, suppose you have an array of n elements. So, let me think. Do y'all remember the explanation he gave for this one? I know it was like some weird thing, but here it's saying that you can't have a counter. I think when he did it, he had a counter for the left and right or something. So I don't remember. Something about left pointer and right pointer swapping the true and falses. Yeah, I think it was something like that, but he was saying that we can't. Actually, that doesn't consider a counter as a pointer, so that would work. So what we can do is, yeah. So this is what we can do. We can say set a counter to the left and right of the array. Okay. And then from here, we want to iterate over each. Actually, we want to iterate over the left and the right at the same time. And when they intersect or go over each other, then that means that we've gone through the entire list, which is O of n. A pointer for true and a pointer for false, and then swap when they reach a true and false. Then they keep going till they meet. Yeah, basically. Right? So let's say we have this array here. We want the false on the left? Yeah, so the falses are on the left. So let's say it's something like this. Say it's false, false, true, false, true, true, true. Okay. We're going to start the left pointer here and the right pointer here. Okay. And we're saying if this is false and this is true, continue going. Okay. So we're going to continue going over here and continue going over here. If this is false and this is true, which it is, we're going to continue going. So boom, boom. And now it says if this is true and this is false, but here it's true, true. Okay. So then we have to think, what do we do here now? Because we can't just simply swap them. We could if this was false. If this was like false like that, then we can simply just set this to false. And then we could set this to true. Right? But here we can't do that because now it's true, true when there's a false right in the middle. So what do y'all think? What should we do here? You're saying move the right pointer? Oh, true, because the true is supposed to be there. Right, so what Zainab said is that, yeah, move it to the left. Sorry, it's because I did the backspace. So if we had a true on the left and a true on the right, then we're going to keep moving this right pointer to the left until we hit a false. Once we hit a false, then we make the swap. So then this becomes false, and this becomes true. And it would be the same scenario if, let's say, it was false, true, false, true, true, false. Okay, so let's say something like this. Arrow, arrow. Right, so what we have is false, true. That's good. So we're going to move over 1 and move over 1. But here we hit false, false. Right? The left is supposed to be false, so it's fine. But the right is false, which is not supposed to be. So we're going to keep moving the left pointer. False, false, still. Move it again. False, false, still. Move it again until we hit a true. Once we hit a true, then we make that swap. So boom, boom, false, true. Okay. Once that's done, then we increment both of them, and they both land in the same spot, so it's fine. And that would be the algorithm. Based on this, I'm guessing he'll give us some kind of problem that will require us to pick one of the algorithms, but tweak it so it fits the question. This is like quicksort, but true or false. Yeah, basically. Pretty much. So, based on that, we could put as our answer, set a, I don't know why I put counter, set a pointer to the left and right of the array, okay, and, oh, fuck, what just happened? Okay. Iterate both counters, oh sorry, not iterate, increment. Both counters until, sorry, both counters while while right until points to false, then swap. Okay. And then finish when left is greater than or equal to right. Okay. And that is the answer to that. That would be O of n. Okay. Any questions about that? No questions about that. Okay. Not too bad of a question. Now let's move on to number 4. And this is a code question. Doesn't apply to our code question, but it's still good to go over for practice. So, this one's saying consider the following partial code for a binary tree. We have the class tree, which just contains a root and the constructors. And then tree node, obviously we have our value, our left child, right child, and then our constructors. And it's saying here, the following is a method to invert the tree, e.g. if it's a BST from lowest to highest, make it go from highest to lowest, write the missing code. Oh damn, this is a weird question. If it's a BST from lowest to highest, make it go from highest to lowest. Okay, so basically it's not saying it's not saying to go from this to this. It's saying invert the tree if it's a BST from lowest to highest. Yeah, honestly, I'm not too sure about this question. Smimmy says, should we skip this question, do the ones relevances again? If you want to, we could. But we don't have to answer this question, but does anyone even have any idea on how to answer this question? Because I actually don't even know. Invert tree. I think it's saying make the... Lowest to highest. How can a binary search tree be lowest to highest? Yeah, I'm not too sure. Bigger numbers on top. I think it's saying like if it's like this is the lowest number, then it goes from lowest to highest. Turn it into highest to lowest. So kind of like that. Where this node is on the top. I think that's what it's saying. Create a temp variable to store left and then swap it with the right, maybe. Well, that would be just to do this. That would do that. But okay, so it's not a BST, so that'd be valid. But you said 518815. Yeah, it'd be something like that if it's from lowest to highest. But what if it's like the root is like 3, 4, 5? Then what? So I'm not too sure. I don't know. I do not know. Because if it's lowest to highest, then you would have to get this node here and then make what's here its children. Like that. Hold on. Let's see. Was there an answer here? Luckily, this is not on our exam, so. Okay, this is what they did. If node.leftChild is not equal to null. Oh, it is just swapping. Okay, I think this part here where it says e.g. it's BST from left to right, I think that's what makes it confusing. But I think it is legit just doing 3, 4, 5. Because if we go here, we are just making an attempt to store the left child, setting the left child to the right child, setting the right child to the temp. So that'd be it. But I think what's really confusing is that EG part. I don't know why he did that. Anyways, let's do number 5. That question is thankfully not relevant to our exam. Right. So I think this is a choose the data structure question or something. I didn't get to read it. I was covering my eyes so I don't see the answer. Okay. So this one says, for each of the following scenarios, state whether you would model it with an array, linked list, doubly linked list, or array list, and explain why. Okay. So part A, it says you run a bowling alley and need to keep track of who is in each lane. Okay. So for this, I personally would choose an array. Yeah. Let's notice that an array. Because we can have each index be whatever row, and then we just have one group of people at that index, right? So I would say array. And the number of, like he said, the number of rows do not change. So you can say a an array. And if there can be multiple people at a row, you can simply just make an array of array list and then just add to that index of the array list. Sorry, index of the array. Okay. B, if all lanes are occupied, you keep a waiting list, first come, first served. Okay. So we're saying that we want to lanes are occupied, you keep a waiting list, first come, first serve. I would say, well, we can't just say queue because it says array, linked list, double linked list, or array list. That's not an option. So I would say double linked list. Yeah, what Soft one said. Because with a queue in Java, well, this is just like if you know about Java, then you'll be able to get this. With a queue in Java, that is implemented with a linked list. And linked lists by default in Java are doubly linked lists. So just from that, you get the idea that a queue is implemented using a doubly linked list. But I'll actually explain why. So with a doubly linked list, you're able to remove from the front and the end in O of 1 time. So let's say someone gets onto the list or the queue, right? They get on the waiting list, right? And it's first come first serve. So they get on the waiting list and they're in the front. Then to add another person to that, it's still O of 1. Add another person to that, it's O of 1. Add another person to that, it's O of 1. Okay. Now let's say a spot opens up. We can simply just shift the head over by one node, okay, and then set its previous node to null, and then that will get rid of the first person, so that's O of 1. Okay, and then if someone wants to get off the list, say, hey, this list is too long, I'm just going to go home, right? Then you just set the tail equal to tail.prev, prev being the previous node, and then set tail.next equal to null, and that will get rid of the last element on the linked list. That's why for B, it'd be a double linked list, and for A, it would be an array. Okay. Are there any questions about that? Would just a normal linked list work too? No. A normal linked list, I mean, you can, but it's asking what would you model it with, and you're given those choices, you have to go with like the best choice. You can do it with a linked list, but if you want to remove from the front, right? That's what? If you want to remove from the front, that's O of 1 time because you could just shift the head over, right? But to remove from the end, that's going to be O of n because you have to go all the way to the end, then set then set the one right before the next, set the one right before the last node to null, and then that would remove from the end. So to remove from the end, it would be O of n. Remove from the front would still be O of 1, but you want to choose the best. Would you have to explain all that, or is it enough to say you would use a queue, which is implemented using a double linked list? I wouldn't say you would use a queue because it says linked list, double linked list, or array list. I just use that because that's what I first picked up on, but for my actual answer, I would have put what I just said. Where you can say a double linked list because you can remove from the beginning of the list and the end of the list in O of 1 time, and you can also add to the beginning of a list in O of 1 time. Same thing with adding to the end of the list. Okay. And we can double check that if we go over here to list. And we see here that adding and removing from the front is O of 1, and adding and removing from the end is also O of 1. Of course, adding and removing from the middle is O of n, but you're never going to be adding and removing from the middle because it's first come, first serve. It's either you're taking the person off of the beginning of the list because it's their turn, or taking someone off from the end of the list because they don't want to be on the list anymore. So we're just dealing with O of 1. Okay. You don't want to use an array list. Of course, you can do O of 1 removing from the end, but O of 1 removing from the front, which is first come, that would be O of n, so we don't want that. And linked list removing from the front is O of 1, but removing from the end is O of n, because you would have to traverse the whole thing. And let's say someone gets off the list, let's say we have this long list, right, of names. We don't want to say, hey, okay, let's find this person. Where is he? Where is he? Where is he? Oh, he's right there. Okay, let's take him off. Right? We don't want to do that. We want to just do it in constant time. Like, oh, you're the last person on the list? Okay, you're gone. That is a doubly linked list. Okay? So that is the answer to that question. Are there any questions about that? That's 20 points. That's a good question to think about. Any questions about that? Right. I'm surprised that's worth more points than this one, but whatever. Okay, let us find number 6, right? Yep, number 6. And this is testing our traversals, which I wouldn't be surprised if the traversals are the mystery questions. So make sure you understand this. We also getting this? Yeah, we are. But instead of list, it's what? It's priority queues, AVO tree, stack, and what else? I don't know what else there is. I think that's all there is. I mean, probably important to understand when you want to use data structure. Yeah. Oh yeah, hash as well. I don't think stack then. It's because it was only 5, right? Queue, priority queue, hash, AVL tree, and stack. Oh yeah, that's 5. Okay. All right. So number 6. We want to list the order of the vertices as visited in the tree below. So we're using this tree here, and we have to do at each point. Okay. I doubt he supplied this where it says left, right root. That's literally giving the answer. I doubt he supplied this. I think this is whoever was using this exam. They put it themselves. So I'm going to do that. Because no cheating. Mystery's only theory question? Yeah, so I feel like for mystery, I think it could be one of two things. I think it could be tree traversals or recurrence relations. Either one, I think. So be prepared. But again, don't go off what I'm saying. Be prepared for anything. Yeah, master theorem. Because he hasn't tested on that once, so I would not be surprised. I doubt he would give an AVL rotation question, though. That'd be fucked. Wasn't that like a quiz question? It was, but he can give something different. You never know. He can give like a weird ass code and be like, hey, write the recurrence relation for this, and then also give me the runtime. He didn't do that on a quiz, I don't think. Or he gave code. I don't think so. All right. So, post order. I'm going to write it here. post order is we're going all the way to the left, then the right, then the root. Okay. So we're going all the way to the left. We see we hit left is null. So then we're going to the right. That is C. So boom. Once we hit C, we see that left and right are nulls. We go back up to the root and say B. Now, again, the root is last, so we're going to go to the right of the root, and we see we hit a null. Sorry, we hit a node with a left, so we're going to go all the way to the left and put the E. Then we're going to go back upwards because left and right are null. We're going to ignore the root for now, go to the right. Since this is not null and those children are null, we're going to say F. Oh, F, then go back up to the root, D, then go back to that root, A. So the answer for this is CBEFDA. Okay. Makes sense. That should be good. Someone's typing. Yeah. Okay. B. In order. What in order is doing is we're saying go all the way to the left, then hit the root, then go all the way to the right. So we're saying left, middle, right. That's in order because we're going left to right. Okay. Meaning we're not going to start with the root first. We're going to go all the way to the left. We see left is null, so then we do the root. That is B. Then we go all the way to the right. The only thing that there is C, so C. Then we go back up to the root. That is A. Then from there, we go all the way to the right. We hit another root, so we're going to go all the way to the left of that root. And we get E. Then D. Then F. And that should be good. A, B, C, D, E, F. Okay. Does that make sense? Easier to way to look at in order is just look at the nodes horizontally. Horizontally. BCA. I don't know what you mean. From left to right. So you're saying like this. Like read this way. B, C, A, E, D, F. I mean, you could, but in this picture here, it kind of looks like the A is aligned with the C, so I feel like that could kind of be hard to look at. But if they weren't aligned, then it'd be B. Well, actually, no, it would be whatever's here, then B, C, A, E, D, F. So I think that could work. As long as the graph is drawn good. Yeah, the root comes after left. So it's left, root, right. In order. Left, root, right. And then finally, BFS. This is the easiest one. It's just level order. So it's just A, B, D, C, E, F. That's it. Right? Because we start at this level, we say what's at the level from left to right, it's just A. Then we go to this level, we say what's on this level from left to right. That's BD. Then we go to this level and say what's at this level from left to right. CEF. So A, B, D, C, E, F. Okay. And we'll just do one final practice. Let's do pre-order. I feel like pre-order is the easiest DFS one. That would just be A. That's all the way left. So A, B, C, E, D, F. That should be correct. That's correct for pre-order, right? A, B, C, E, D, F. Actually, wait, no. No, it should be A, B, C, D, E, F. Sorry. Yeah, there we go. My fault. Because it's root, left, right. Yeah. Okay. What I like to think of with pre-order is that we add or print whatever route that we're at before moving to the next one. So right here, we're at A, we print it, then move to the next one. Once we hit this one, we print it, then move to the next one. It's null. So we go here, print it, then move to the next one. Nothing there, so we go back here, go to D, print it, then move to the next one, so it'd be left. Print it, then move to the next one, nothing there, so we go here, print it, then move to the next one. That's why it's A, B, C, D, E, F. Okay. All right. And then number 7, perform Prim's algorithm on the graph below, starting at vertex 0. Draw the MST after each vertex is added. Okay. Can you go over a recurrence relation loop question? I really don't like. I really do not like recurrence relations. We'll see. This is the same exact graph we just did. So do y'all want to do this one? No. Yeah, this is literally what we just did, just with different weights. It's okay? Alright. So that should be it. Is that coming in the exam? Well, we don't know, because it could be anything for the mystery question. So there's no way of knowing if it could be on it. So I have no idea. All right. But if you want to look at it, we can really quickly. But I'm not even gonna memorize this shit. I don't care about this. Okay. What the fuck? I don't even remember doing this. Let's skip this. Matryoshka? Oh, okay, that's dolls. You don't have to know this. We do not have to know this. Oh, wait, we could get one of these. Actually, no, we had this as a quiz question, right? No, so we wouldn't get that. We never had a quiz, right, where we were given code and we had to write the recurrence relation. That was never a quiz, right? I would say it's safe to assume that Unbreakable. Don't think so? Okay. That was just a practice problem? Okay, so I wouldn't be surprised if he gave code and he said write the recurrence relation or give the runtime. So be on the lookout for that, I guess. Right. Hold on. Give me 1 second. Okay. He did examples in class, though? He did. So I don't even remember how to write a recurrence relation. So I wouldn't even be able to, I wouldn't be of much help for this. Let's see. I remember I wrote like a formula here or something. I like completely blocked this shit in my mind. Yeah, if he gave something like this, I'd kill myself. think it's reps. Order functions. Where is master theorem? There it is. So where's the formula? Okay, so right here we have that whatever's to the left of whatever's to the left of T is the A, whatever's under the N is the B, and then you can have N to the K log whatever, right? And then from that you're able to derive this portion here. Yeah, I wouldn't even recommend unless you need like a 100 to pass this class, I wouldn't even recommend studying that hard for the mystery question. I'd recommend mainly focusing the 4 questions that you know what the topics are going to be on. Okay? So that's my advice. So that's why we're not going to do this. Because if you want that, you can try that on your own time. All right. Is there anything else? I don't even know. We don't have to know. We don't have to remember like hashing with chaining and all that, right? I don't think so, right? No. Okay. Nope. All right. Trying to think what else it could be on. Obviously, no. He said 100% for the pick an algorithm. Sorry, pick a data structure one. That's going to be stacks, AVL trees, queues, priority queues, and hash tables, right? He said that 100% or no? Because if not, then you guys should. I wrote in my notes stacks, queues, and AVL. Okay. So obviously know when to implement them. Actually, wait, for hashing, does the code work any different for hashing with chaining versus linear probing? Yeah. I think I have the code here. Hold on. Did we do the code for that? I don't remember. Okay, we didn't do the code for that. But the code that I gave, right here, I think that was for... I believe that was for hashing... I think that was for linear probing. I don't know where my code went. Oh, here it is. So yeah, sets... Okay, no, this was for hashing with chaining. So that's the code. My code is hashing with chaining, and he never gave code for linear probing or anything like that. So I doubt he expects us to know that. Do we need to study array, linked list, W linked list, or array list for the scenario question, or just the ones in the review sheet? Well, again, I don't know if anyone confirmed it with him. What is data structure for Discord message conversation? Stack? That would not be a stack. Yes, it'd be a queue. First person to send the message, that gets sent. Okay, so I guess we can do like those scenario questions one more time for fun. I will have ChatGPT give us randomly generated ones, and then we will answer them. So let's bring that up. I mean, the chat wouldn't be a stack either. because the newest chat goes in the bottom. All right. So I'm going to put this in GPT, and I'm going to say, give me. I'm going to be specific with it too. Give me questions involving these data structures. Do not tell me what the question applies to. Just give me 10 questions and nothing else. Okay. So let's see what we got. Vertical queue. Okay. All right. Okay, these look good. So let's see if I can get these all in one picture. And hopefully there's no discrepancies here. All right. So I'm going to write in white. Okay. All right. And what we have to choose from is. Thank you for sending it, Snow. What we have to choose from is stack queue, priority queue, AVL tree, or a hash table. Okay. And the first question says, which data structure would be best suited for organizing elements where each element has a different priority and you need to always remove the element with the highest priority first? And that's kind of a giveaway. Priority queue. There you go. Priority queue. Okay. All right, number 2. Which data structure should you use if you need to ensure that the order in which elements are added is the same order in which they are removed? Man, what the fuck? This is not like scenarios. Okay, this is annoying. Hold on. Let me, I gotta be more specific with it. For each question, apply a real world example. Just like how it was in the questions I supplied. ChatGPT moment. Okay, now we got some real things. Honestly, so that y'all will be able to actually understand the definitions, I feel like we should still go through this. So, what data structure should you use if you need to ensure that the order in which elements are added is the same order which they're removed? Obviously, that's a queue. First in, first out. Okay. Next, if you need to frequently check if an element is present in a collection and you want this check to be as fast as possible, which data structure would you use? That is a hash table. Okay. In a scenario where you need to maintain a collection of items in a balanced manner to allow for fast searching, bro, this. Okay, AVL tree. Should get on all my nerves. Which data structure would you use if you need to add elements in such a way that the most recently added element is the first one to be removed? That is just a stack. and that is LIFO. Last in, first out. Okay. If you have to handle a sequence of events, each with a specific time associated with it, and need to process these events in chronological order, what data structure would be most efficient? If you have to handle a sequence of events, each with a specific time associated with it, and need to process the events in chronological order, this would just be a priority queue. Now, it kind of depends if you're adding each of those events into the queue at the time that it happens, then it would just be a queue instead of a priority queue, but it doesn't specify that, so I would say a priority queue. That's why it kind of tricked me up for a second. All right. For a situation where you need to match pairs of elements, like opening and closing bracket, bro, and always need to match the most recently added opening element first, which data structure is ideal? That is just a stack. When implementing a system where you need to associate unique keys with if you have a collection of items where each item needs to be uniquely identified by a key and you want to perform a very fast lookups, this is just repeating itself now. In a scenario where you need to process elements in the order they arrive, ensuring that the first element that arrives, that's legit the first. Okay, that was just a repeat of the first. All right, so this should be ready now. Oh, fuck. Refresh. Depends. Depends, Nylam. It depends on the question. What's the difference between hash map and a hash map is a hash table?
They're essentially
Don't-
the same thing, but they just have a different name for some reason.
Well, it's not for some reason. For hash map, it's what's being mapped is the key, and that key corresponds with a value, right? A hash set, that would be most close to the definition of just a normal hash table, but obviously there's different applications for all of them. So again, you know how hash table can be some interface, and then hash map, hash set, tree map, all those different kinds of maps, they can inherit hash table. Yeah, unbreakable, yeah. Yeah. It's not my money, so I don't care. All right. Let's go there. Right. Hopefully we have some better ones now. Oh, fuck, this shit just flashbanged me. Okay. So again, we are working with hash tables, stacks, queues, priority queues, and AVL trees. So number one, in a hospital emergency room, patients are triaged based on the severity of their condition. The patient with the most critical need is treated first, regardless of the order of arrival. This one is pretty simple. What do you guys think it is? Just, yeah, priority queue. So I'm just going to write priority queue right here. Right, and then obviously for this question, we would have to give the data structure and the explanation. So can someone give an explanation as to why this would be priority queue? Most critical need. Well, answer it how you would answer it on the exam, just to give yourself some more practice. So what do y'all think? If they need urgent care, you would assign a higher number to them. Or basically, you could just say that you're dealing with patients that have higher priority than others, and you want to treat them first. And for that, you use a priority queue. That works too. That'd be a good explanation. All right, number 2. At a bakery, customers take a number when they enter. They are served in the exact order they arrive. What data structure should be used to manage the system? Q? Correct. I'm just going to write, there's no room here. I'm just going to put a Q. And also, just make sure you spell Q correctly. Yep, first in, first out. All right, number 3. In a library system, you want to quickly... sorry. Oh my god. What the fuck did that come from? My fault. Alright. That was disgusting. My fault. Number 3. In a library system, you want to quickly check whether a specific book is available or not. Given the large number of books, which data structure would be the most efficient for this task? Hash table. Right? Because we have a large number of books. We want to be able to look up which book that we need in all one time. And that can just be done with a hash table because each book is hashed to a certain location, and you can find that location using a hash table. All right. So I think when it comes to like looking up for these questions, it's either going to be an AVL tree or it's going to be a hash table. Okay. Because if you're looking up an exact thing, that's going to be hash table. But if you're looking up something that's near a certain other thing, AVL tree. Okay. All right. Number 4. In a contact management app, you need to store and retrieve contact information such as names and phone numbers efficiently, with the ability to add and remove contacts regularly. Which data structure would be the best for this?
I believe it would be wait, first taken.
Olivia,
So
array.
first out, so that means it's Q's.
No.
Yeah. For number for number 5 or number 4?
Number 4.
Oh, I'm sorry. Hold on, I'm reading it wrong.
Okay, you guys are giving answer choices that aren't answer choices. The answer choices are stack, queue, priority queue, AVL tree, and hash table.
I believe it's hash table.
It's just hash. There you go. Right, where the hash, the key can just be the name, and the value can just be the phone number. And you can add and remove that in all of one time. So it's hash. I wouldn't, honestly, I would just keep the answer as hash table, but you can elaborate that it'd be a hash map in your explanation. But don't say this would be a hash map. Say this would be a hash table. All right. In a stack of plates at a buffet, the most recently washed plate is placed on top, and the first one to be taken by the next customer. Which data structure represents the system? It says it in the question. Stack. Okay. For scheduling tasks in a computer system, when tasks are executed based on their scheduled time, what data structure would best manage the sequence of these tasks? I wouldn't be surprised if he makes ChatGPT write some of the questions. It says for scheduling tasks in a computer system where tasks are executed based on their scheduled time, what data structure would best... Okay, so yeah, I'm pretty sure it would be priority queue. Right, because they can start to execute at the same time, but if there's one application that has a shorter scheduled time, then that's going to execute first or finish executing first. Okay. Wait, would just be queue if you're putting them in order? Well, it's not guaranteed that they are in order, so you don't want to go off of that because you can start an application first that takes a long amount of time or a long amount of scheduled time. And then the first one, let's say you put in a second one, and that has a shorter schedule time, that one's going to finish executing first. Right? Mm-hmm. All right. In a code editor, which data structure would be ideal? Q should only be considered if the question. Yeah, there you go. In a code editor, which data structure would be ideal for checking the correctness of parentheses, ensuring that. Okay, we just did this one. I like how I said make a real world example and then GPT just added in a code editor. All right. In a shopping website, you want to quickly find the details of a product like price and description. It didn't get to finish, but yeah, this is just hash. More specifically, hash table. I'm convinced Steinberg uses GPT for those questions. Yeah, probably.
Wait, he would really GPT them?
Well, I don't know, but they sound like GPT scenarios. It didn't give an AVL tree one. Yes, it did not. I think it's because it didn't finish. Yeah, let me refresh it again. This is the third time it's crashed. Or sorry, second time. Let me see if it gives one now. When would you use an AVL tree? So there was a question that he gave. It was like, you're in a winery and you want to find a wine that is close to $50, right? Then you can just search an AVL tree to find $50, all right? And if you don't find $50, then you can just find whatever's closest to that, right? So let's say your first root node is 40, then you're going to just go to the right, and then just find you know what I mean. But yeah. Let's check what it gave now. Okay, they didn't give any AVL tree ones, but yeah, you know what I mean. All right, I'm gonna give my own one now. Let's say, and what the ones I'm about to give, they can be answered with any data structure, so it doesn't have to be the ones on the list. Okay. So, let's say I have a can of Pringles. Yep, exactly. Stack. Right? Because if you reach in, you got to grab the first one that's at the top. But let's say there's a hole on the bottom too, and I can grab from the bottom and from the top. Not a queue. Doubly linked list. Right. There is a type of queue that'll do that. It's called a DQ, but he didn't teach that. Where DQ you can remove from the front and the back. Right. But since he didn't teach that, we're just gonna say doubly linked list. Okay. Here's another one. This is me. Okay. And I'm walking into a computer store. And I find a guy, the depressed Micro Center worker, and I say, give me cheap NVIDIA card. What would it be? AVL tree. Right, obviously there's no such thing as a cheap NVIDIA card, but I'm saying, the cheapest, right? So that can be done by going to the root of this AVL tree that would have the average price or whatever at the root. Then we could just go to the left and see whatever's the leftmost node and then just return that price. Okay, so that would be an example of an AVL tree. Does that make sense? Okay, I'll move that over there. Let's think of another one. Let's see. I'm in line. I'm in line at the grocery store, but I'm sad because this long ass line has long ass people. Sorry, not long ass people. This long ass line has a bunch of people that they're also waiting online. Okay. But then I'm like, wait. Wait, I have a BJ's card. And since I have a BJ's card, now I'm happy. Because I can just take my ass. I'm skipping all these people. And now I'm at the front. So the answer, yep, correct, Lauren. Priority queue. Because this line gives priority to people who have a BJ's card. Okay. Right. And that is priority queue. Yep, you just fucking destroy that line. No, you can't do that in BJ's. to shop at BJ's, you have to have a BJ's card. If you don't have a BJ's card, you get like charged more. Or something like that. Which I'd even know. I went to BJ's with my parents one time, and they're like, "Yeah, you didn't know that." I'm like, "What the fuck? I didn't know that." That's very weird. Yeah, that's what they were saying. You don't have to have one to shop there. You can still shop there, but if you don't have one, you're gonna get charged more. That's the same with Costco. It's the same with all these other places. So yeah. All right. And that's why BJ's and shit. That's why they make a lot of money, because if you have a card, you can get a lot of stuff for the wholesale price. No, you can still shop there. You'll just be charged more. At least that's what I was told. I don't know. All right, let's think of another question. Let's move these over. Let's see what else we can conjure. Let's move this. Okay. What would be the situation for a linked list or an array list? I think the thing is I can't even think of one, because with linked list and array list, there's like better options. Like for a linked list, just use a doubly linked list. But let me think for a linked list. Let me think. Okay, let's try this. This is pretty inefficient, but let's try this. So let's say I just skipped everyone in the line, and now I'm happy. But I got this big ass cart, and it just has a lot of shit. Right? No, it's not recorded. Right? This has a lot of shit. And I am now putting this stuff on the conveyor belt for the depressed worker to take. Okay? And I'm putting them on one by one. Boop, 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 boop. But let's say that she's taking them one by one. So she's doing that one, then that one, then that one. But then let's say all of a sudden I say, "Hey, stop taking them from the front. I have a coupon for this one. I want you to do this one first, because I have a coupon and I want you to do that one." So she's like, "Ugh, fine." She goes, takes this one, puts it over there, she scans it, and then these come forward. What would this be? Not a priority queue. Wouldn't be an array list, it'd be a linked list. Right? If it was a priority queue, then anytime we put something on the conveyor belt, they would have automatically been in the order if I had a coupon. But with the linked list, I'm saying I'm putting everything in no order, and then I'm telling the computer, I'm like, hey, actually, let's take that one out from the middle because I have a coupon and just do that one right now. And then it shifts everything over, and it does that one first. Again, if it was a priority queue, as I put stuff on, it would have already been in order. Okay. So that's why this is a linked list. Now, this can be done with an array list as well, but that would be way more inefficient. Because, let's say I remove here with an array list, then I would have to shift all that over. Right? Because you can't remove from the front of an array list in O of 1 time. That's done in O of n time. Okay? That's why it would be more efficient to do this with a linked list. Obviously, you can do this with a W linked list, but Lauren asked for a linked list. That's why I did it with a linked list, but obviously this would be even better with a W linked list, because let's say the last thing I put that has a coupon, so I say, hey, take this, and I just like, take it from the back, and I just fucking throw it at her, and she does it, right? That'd be a W linked list. Okay. But yeah. Any questions about that? What did we go over so far today? We went over BFS, DFS, Prim's algorithm, and Dijkstra's on graphs. Then we did BFS and DFS on trees. Then we went over the runtime for those. Then we did an example exam, and then now we're doing this. Would there be any instances when an array would be better than a hash map for lookup? Not when you have a lot of space, but when you have a set amount of items. So let's say there's only 10 items, right? Or let's say there's only 3 items. And when you want to know what's the third, you can just say erase of 3, right? With a hash map, you would have to first hash it, then do all that stuff. So can you for hash? What? So that's why I say I would say that an array would be better there if it's for a lesser amount of things being used. But if you're using a large amount of things, I would say hash map. Yeah, you can search by hashing it too, but that'd be kind of a waste of space when it's a small amount of numbers that we're working with. Yeah, both of our 1 access time, but it's if we're working with 3 elements, then there's no need to make an entire hash map when you can just make a 3-element array. That makes sense. So what if you know you have 500 things? Well, if you know you have 500 things, then yes, you can do in a 500 size array. That's good. You can do that. But let's say you have 500 things and then you also want to add something else, then you wouldn't want to use that, right? And that would be only if you have 500 things and let's say you have 500 things and you know they're mapping already, then it'd be then it would be an array. But if you don't know their mapping and you want to do lookups, then you have to sort through the entire array. That makes it hard. So you can just do a hash map. But let's say the question says, let's say you put 3 things in an array in order, and you want to know what's the third thing that you put. Just sorry, not like that. Let's say you have 3 things and you put them on a table, where that table can only fit 3 things, and you want to know what was the third thing you put. You could just use an array, right? Because you just say a race of 3. That's what you put, right? Let's say you don't know that mapping and you're not putting them in order, then you need to do a hash map, because then it will make the mapping for you. Or sorry, hash table. All right. Any other questions? Anything at all? We can quickly touch on another topic if you want. Doesn't have to be any one of these. You're thinking, all right. Wait, the midterm for you guys for the later class was out of 8? Is that true? That's fucked. Wait, no. The midterm for... Wasn't the midterm for the earlier class, wasn't that out of 9? Or something? Pop quiz, worst case for quick sort? That's O of n squared. Yep. Out of 6, is that like before the curve or something? I don't know how it works. Not sure. After curve? Okay, that makes sense then. Out of 18 before the curve, what the fuck? Where are you pulling these numbers out of? Alright, I think that's basically it. Is there anything else we have to do? Again, after this call, I'm gonna eat and then I'll make the Quizlet. Which I don't know if that'll be much of help for people in the earlier section, but yeah. Sorting algorithms. I mean, I could quickly go over the runtime again. Where is it? I think it's over here. Okay, so yeah, if we said the runtime for bubble sort, obviously that's already, if it's sorted, that's O of n. But the average and worst is n squared. Another pop quiz, worst case for a heap sort, that is just n log n, I think. Yeah. Okay, insertion sort, that is also O of n, because you're just doing one iteration and you're checking if what's in front, where did that have to be put in our left array. If it's already in sorted order, we don't have to do anything, so it's O of n. And then average and worst n squared. But selection sort, all of them are still n squared, because for selection sort, you are starting in the beginning and you're looking through the entire array to find the minimum number, and then you're putting that at the beginning, right? Or whatever index you're at. You're swapping them, right? But if they're already in sorted order, you still have to do that. You just don't have to do the swap. The swap is not what makes it long. because the swap is just O of 1, but searching for the minimum number, that's what makes it long. That's why it's still O of n squared. Okay. If I recall, I don't know if that's what you're saying, he said for selection sort, you always have to do n minus 1 iterations, no matter what. Yes. Yes, you do. That's correct. Right, and then heap sort, average and worst, we already know that's n log n, but if in the best case, we know that if it's already sorted, we have to turn it into a max heap, so that is O of n time to do, and then from there we have to do the remove max operation, that's log n, and you're doing that n times, that's why it's O of n log n. How would you check if a graph is balanced? I think you would have to make an algorithm to check the height at each node, maybe? I don't know. No, actually, no, that wouldn't work. Would that work? Yeah, check the height. Yeah, so the algorithm would be something like this. Okay. So, here, we're going to start at the root, and we're going to check the height of the left and right tree. Okay. Check the height of the left and right tree. And we see that that is going to be 1 for each. And they can't differ. Sorry. If we do 1 minus 1, that's 0. So I think that's fine, right? I don't remember how the fuck to do it. But that's 0. Okay. Then if we check these parts here, now we have to check the height of these. So that's 0 minus 0, that's still 0. And check the height of these, 0 minus 0, that's still 0. But let's give a different example. Let's say it was like this. Okay, so we see here the height is 1, 2. We see here the height is 1. Wait, no, am I tripping? Hold on. Fucking how I hate these things. How do we... That is balanced, right? Is it? Isn't it unbalanced here?
No, the height of the left tree is 3, and the right is 2. But the node to the left of that's unbalanced.
Yeah, so this is 1, 2, 3. This is 1, 2.
So that's fine. Sorry.
So it is balanced here, and then 1, 2, and this is 0. It can't have a difference of more than 1, right? So that's what makes it. So this is 1, 2. This is 0, so that makes it unbalanced. And then if we were to check this side, this is 1, this is 1, 1 minus 1, that's 0, so that's good. Okay? But it can either be 1, 0, or negative 1. If it's anything less than negative 1 or greater than 1, so like 2, 2, 3, 4, it's unbalanced. Okay. So what I will recommend is at each node, find the lowest depth of each of its children, right? Or sorry, at each node, check the lowest or the highest depth, I don't even know what you would call it, check the maximum depth of its left subtree and its right subtree. And if that depth differs by more than 1, then it's not balanced. And if that depth doesn't differ, then we recursively move to the left one, do this one. Then if let's say that's good, then we do this one. Let's say something's here, then we do this one after, and so on. So convert the graph into a tree and use DFS. Oh, you were saying for a graph, not a tree? Gotcha.
Question are you doing right now? Question 2?
Yeah. So yeah, I would say to first, if it's a graph, first check for any cycles. Okay. If there's any cycles, then you can just ignore it because that's not balanced. That's not even a tree. Actually, I mean, what defines a balanced graph? That's what I'm not too sure about. Let me see. Give me 1 second, because I don't know if the definition differs between a balanced graph and a balanced tree. What is a balanced graph? If every induced cycle has length, what does that mean?
For our purposes, I'm not sure there is a definition. I'm not sure if a balanced graph even is a thing.
Let me check the images. Okay, this is something else. Hold on. Let me look up data structures. You know, I don't think you testing for balanced graph. Yeah, that's what I'm saying. I don't really know what a balanced graph is. I don't think he ever talked about that before. So if you were to ask something like that, I would say first convert the graph to a tree. To do so, test for cycles. If there's no cycles, then convert to a tree using Prim's algorithm, I guess. I don't know. Using Prim's algorithm. And then at each node starting at the root, check for the maximum depth on the left and right subtree. If they differ by more than 1, then it is not balanced. That's what I would put, but that's probably wrong. Honestly, we can just ask. Let's see what good old ChatGPT wants to say. How do I know if a graph in data structures is balanced? Let's see. A graph is either directed or undirected, and it's either weighted or unweighted. All right, in the context data structures, the term balance can apply to different types of graphs and tree structures, each with its own specific meaning. However, the concept of balanced graph isn't standard. Okay, so I don't think that exists. I think you'd probably ask, is a tree balanced? Term is more commonly associated with trees, yeah. Balance refers to the property that ensures that the tree is reasonably well proportioned, so operations like the insertion, deletion, and lookup. Okay. So that's what I would say. I think he would ask for balanced tree, not balanced graph. Okay. And then let's say he asks, design an algorithm to see if what would be adjacent or connect for graphs. Well, adjacent is if two vertexes are connected by an edge, but connected is like they're not exactly next to each other, but they're connected by some path, right? So you can be adjacent and connected at the same time, but you can't be let's say you're just connected and not adjacent, that's also valid. So let's look up a complete tree. Should be a good one to know. So it says a complete binary tree is a binary tree in which every level except possibly the last is completely filled. Right? So what I would do for this is I would say do BFS until you're at the last level. And once you're at the last level, ensure that nodes are filled from left to right. So if there's ever a part where the node left is not equal to null, if the node left is equal to null and the node right is not equal to null, then that is not complete. Okay. And then similar to that, we have perfect trees.